In the last lecture, we talked about photoelectron spectroscopy, and we looked at the POGLE related to that, or we will if we haven't yet. And what we saw from that is that unlike the Bohr model, which suggested that these electrons were in discrete orbits around the nucleus, there must also be some sublevels, because the PES showed like beryllium and lithium electrons, for example, in a different place than nitrogen, oxygen, fluorine. So there must be some sublevel within the second level, okay, suggested by our PES data. So Bohr's equations predicting these energy levels, they really only worked for single electron atoms like hydrogen, and they worked okay for helium, but as we get beyond that, it really wasn't working out very well. And then we have our PES data suggesting that there are subshells. So how are we going to explain that? We do that through the quantum mechanical model. And this sounds complicated, but this is really just using orbitals like we learned in pre-AP. The idea, though, in AP is we had to explain why do we need that? Why do we need a model that has orbitals instead of just saying, oh, there's the first energy level and the second and the third, and that is based on this PES data because that indicated that there were subshells. So the quantum mechanical model tells us that electrons do not follow orbits. So they're not spinning around in these distinct pathways like Bohr thought. The electrons are just moving around and around in a circle. Instead, we're going to describe the electron's movement using what is called a wave function. And so all this does is it tells us where the electron's possible positions are in three-dimensional space. And that area where the electron could be is often called an orbital. So there are multiple possible wave functions, and in pre-AP we called these multiple possible orbitals, and it's the same thing. So there's using different vocabulary here. So you have your 1s, your 2s, your 2p, 3s, 3p. These are not in order. You can also have a 3d, which we know comes after 4s. You can have 4p and 4d and 4f. Again, we know that 4f would come all the way after 6s, if you remember back to pre-AP, and we'll review that in a minute. But this is just telling you these are the possible orbitals. This is not like suggesting the order or anything. But every electron in one of these orbitals has the same energy level. So if we look at the second row, lithium, beryllium, boron, carbon, etc., everyone on the second row does not have the same energy level. However, if their electrons are in the same orbital, like we see here with fluorine, oxygen, neon, those electrons in the same orbital, they actually do have the same energy level. So what is an orbital? All an orbital is an area that the electron will occupy 90% of the time. So the atom doesn't know where its orbitals are. Okay, this is just a label that scientists have put on these areas saying the electron is here 90% of the time. So, for example, if we track the electrons within the 1s sublevel, we'll find that every so often we ping where the electrons are, and we get kind of this mapping of the electrons, and then they say, okay, where can the electron be found 90% of the time? We need to narrow it down, and this is the area where it is 90% of the time in the 1s sublevel, and so that is the spherical sublevel. So 1s orbital is a sphere, and then we can look at the other orbitals. 2p, there are 3 of them, and these are the areas where the electron can be found 90% of the time within that orbital. So there's 3 different 2p's. So if you remember back to pre-AP, if we were doing a p orbital, if we wrote 2p, then we would draw 3 lines, because there are 3 of those 2p orbitals. What does that mean, though? Here's one of them. It's called px. All that means is it's oriented along the x-axis. So if you think about an xy axis, px, okay, be oriented that way. Then there is, of course, py, which is oriented along the y-axis. And then the third one is called pz. And all that is it's oriented like in and out of the paper. So remember, we're talking about three-dimensional structures, but we're trying to draw it on two-dimensional paper. So we have our x-axis and our y-axis, and then you have this one that would kind of be jutting out of the paper, if you could draw it that way, and that would be your z-axis. So those are your three p orbitals, and this just shows them stacked on top of each other. So how do we put electrons in these orbitals? Electrons are added to the lowest energy orbital available. So they would go to 1s first, and then to 2s, and to 2p, etc. And this is because nature always favors lower energy systems. So how do you know where they're going to go next? Well, the periodic table helps us a lot. So you have your 1s, and then your 2s, 2p, and 3s, 3p, and then 4s. And then remember your d values are just one less. So 3d, 4p, 5s, 4d, 5p, 6s, and then we go down to 4f, 5d, 6p, so on and so forth. So you have this table in your notes you can kind of refer to fill out what order these orbitals are in. So based on this, we know that 1s must be the lowest energy because that's where the electrons go first. And then if the 1s gets filled, they'll go to the 2s, which must be the next lowest energy, and so on and so forth. So these are arranged in order of increasing energy. Hydrogen has only one electron, so that one electron would go into the 1s orbital. And that would be written as 1s1 as your electron configuration. The first number is called the principal quantum number. That just tells you your energy level. And then you have your orbital type or sublevel, and then the exponent tells you how many electrons are in that subshell or sublevel. Helium, with its 2 electrons, they can both go in the 1s orbital, because that orbital can hold 2 electrons. So 1, your period number or energy level, s, your orbital type or sublevel, and 2 electrons. Lithium, however, with 3 electrons, all 3 of them cannot go into the 1s orbital. So they're going to go into the next lowest, which will be your 2s. You have 1s2, and then 2s1. This could also be written using the shorthand. And so when we use the shorthand notation, we put our nearest previous noble gas, nearest previous noble gas in parentheses, and then we can add whatever follows that. So helium is 1s2, so we'll replace 1s2 with helium and then write the 2s1, which follows that. Okay, so I put that note there. You can jot that in your notes as well. When you're doing the shorthand, we're using the nearest previous noble gas. Beryllium has 4 electrons, and the first 2 would of course go in the 1s, and then those next 2 could go in the 2s. So 1s2, 2s2, or helium, the nearest previous noble gas, followed by that 2s2. Here you see some examples, just continuing on the periodic table: boron, carbon, nitrogen, oxygen. We're just adding electrons as we go. And then we get to sodium, because neon fills the second energy level. So when we look at sodium, we have 1s2, 2s2, 2p6, and then we move into the third energy level, 3s1. That can be written as neon, which is your nearest previous noble gas, followed by 3s1. Notice that neon is 1s2, 2s2, 2p6, so all we're doing is taking neon and replacing all of that when we do the shorthand. All right, you have some other examples of some larger atoms, such as scandium, which is element number 21. And you can see just some things to note here. After 4s comes 3d. And the shorthand used is argon, which is 1s2, 2s2, 2p6, 3s2, 3p6. Samarium, located way down in 4f. Okay, this is a really large element. That is number 62, samarium. So when you look at that one, some things to note there are that 4f comes after 6s. And you can also go back and see your 4d coming after your 5s, but 4f comes all the way after 6s. And for our shorthand, we would use xenon, because that is the previous noble gas, and xenon has the same configuration all the way up to 5p6. So then we would start after that. Alright, a few rules here. Each orbital can hold a maximum of 2 electrons, and those are going to have opposite directions. When you have more than one orbital in a subshell, for example, P, jot this down as we go, but P has 3 orbitals in a subshell, D has 5 in a subshell, and F has 7 in a subshell. When you have more than one orbital in a subshell, you're going to put a single spin up. This could also be down, as long as it's the same direction each time, is added to each orbital before you start adding the opposite spin. So you put 1 electron with each spin, and then you can come back and do the opposite. And we'll see some examples of Hund's rule. Okay, for example, as we go to lithium, lithium is 1s2, 2s1. So these that are in the same orbital, they have to have opposite spin. And you have to fill up that orbital before you can move to the next one. For fluorine, we have 2 in the 1s, opposite spin, 2 in the 2s, opposite spin, and then when we move to the 2p, we would put 1 up, and then another up, and then another up, and then when we have some more, we come back and do the down arrows. You could also start by going down, 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 and coming back and doing your up arrows. So for nitrogen, with its 7 electrons, we put 2 in the 1s, 2 in the 2s, and then we have 3 left over in the 2p. So this is the incorrect arrangement. This is not following Hund's rule. So Hund's rule says we have to put 1, 2, 3, or 1, 2, 3. We cannot double without having 1 in each of those. So there is the correct arrangement for nitrogen. You place 1 unpaired in each, and this degenerate here, it's a key vocabulary word, but degenerate, or equal energy. Okay, all these 2p's have the same energy, so that they spin in the same direction before you add them in the opposite directions. This creates a lower energy system. Think about these. These are electrons, and they're all negative. And negatives repel, so they don't want to be in the same orbital if they don't have to. So this is going to be lower energy for them to spread out into those 3 different orbitals. All right, some vocabulary words. You might say, how do they know that they spread out like that? Well, if electrons are paired, their up spin and their down spin will cancel so that they're not magnetic. But if an electron is unpaired, it's going to create a magnetic moment within that element. So that's actually how they know whether the electrons are paired or not, is whether or not the atom is magnetic. So first vocabulary word, paramagnetic atoms are atoms that are attracted to a magnetic field because their unpaired electrons cause a magnetic moment. So atoms with 1 or more unpaired electrons are attracted by a magnetic field. So carbon is actually magnetic because it has 2 unpaired electrons. Now, it might not be a very strong attraction to a magnet, but carbon would be affected by a magnet because of its unpaired electrons. Elements that have all of their electrons paired, like you see in neon, are known as diamagnetic. They have no unpaired electrons because their magnetic moment cancels as the electrons are paired, spinning in opposite directions. So key vocabulary: paramagnetic is attracted to a magnet, so you can think it pairs with a magnet. Diamagnetic dies in a magnet, if you want to think of that wording, but it is not attracted to a magnet because all of its electrons are already paired, so it doesn't need to pair with the magnet. There can be some confusion because the word para, we think pairs, so we think, oh, their electrons must be paired. But no, their electrons are not paired, so they will pair with a magnet. They will be attracted to a magnet. All right, kind of switching gears, shielding effect. We talked about this a little bit earlier when we were looking at the Bohr model. But as we add electron shells, so as we go from 1 to 2 to 3 to 4, those successive shells are larger than the previous. So 2s is obviously larger than 1s. The electrons in the successive shell are going to be further away from the nucleus. And they are partly shielded by the previous shell. So the electrons in the second shell are shielded from the nucleus by the first shell. And this shielding effect, this repulsion, reduces their attraction to the nucleus. So they no longer experience the full effect of the nuclear charge, but they experience what is called an effective nuclear charge. So we have Z, effective, is saying the charge they actually experience. It's not going to be the whole effect of the nucleus because they're being shielded by these other electrons. And that is going to be equal to Z, which is the actual charge on the nucleus, and that's just your atomic number, your number of protons, minus a shielding constant. That shielding constant is normally equal to the number of inner shell electrons. Okay, it might not be exactly because there's some other more complicated factors that may come into play, but that shielding constant is going to be close to the number of inner shell electrons. Inner shell electrons, because those are what are blocking this outer electron from feeling the full effect of the nucleus. They're shielding him from it. This effect helps explain a lot of our periodic trends. So we're going to run through these periodic trends and talk about why each of them occurs. So we have atomic radius, ionic radius, ionization energy, and electronegativity. Key vocabulary and key to understand the trends. The first trend is the atomic radius. As you go down the periodic table, the atomic radius increases, but as you go across, the atomic radius decreases. As you go down, the atomic radius increasing makes sense. The atoms are getting larger as you move down, and we'll talk about why. But across stumps people a little bit more. So first of all, let's talk about going down. As you go down, the atomic radius increases because new shells are added. New shells are added. Okay? So here, if we're on the free response portion, which we'll do some free response questions, and you'll be tested on this, why do they get bigger as you move down? And this is the reason. New shells are added. Okay? To go a little further, your valence electrons now have more energy and are further from the nucleus because they're in a bigger shell. They have a greater shielding effect and a decreased effective nuclear charge. So they have more electrons in between them and the nucleus. So according to Coulomb's law, this force of attraction would be greatly decreased because distance is increasing, because of these new shells that are being added, so our force of attraction is going to go down. All right, now across from left to right. Why do they get smaller as you move from left to right? If we look at all the numbers on the periodic table, when you move left to right, all the numbers are getting bigger. The atomic number is getting bigger, the mass is getting bigger, so how's the atom getting smaller? Okay, here's our explanation. The valence electrons are still in the same shell. So their shielding effect from those inner shells is going to be similar. However, we got more protons in the center, so we're going to have a greater effective nuclear charge. So the charge that they feel from the nucleus is going to be stronger because there's more protons in that nucleus. So if you look at Coulomb's law, the charge on our nucleus is going up, which is going to make our force of attraction go up. And as that force of attraction goes up, it's going to pull those electrons in toward the nucleus and decrease the radius. So we could use either of these on a free response to explain. We could say that the addition of protons increases the effective nuclear charge, or we could say, according to Coulomb's law, as we increase this positive charge, because there's more protons, the force of attraction experienced by each electron increases, thereby decreasing the radius. Okay, so two explanations, both saying basically the same thing, but that's two ways you could write that if we were on a free response question. All right, let's talk about ions. So how do we make ions? Particles with charge. One thing to keep in mind is that we cannot lose or gain protons. So to make an ion or a charged species, we've got to change our number of electrons. Cations, remember this is going to look like a positive sign. Cations are positive because they've lost electrons. And these are usually metals or hydrogen. Whereas nonmetals are usually going to form anions. So think the antagonist is usually the negative character in our story. And these are usually going to be nonmetals. So they're going to gain electrons to form a negative charge. So metals on your left-hand side of your staircase, they're usually going to lose. So these will usually be positively charged. Whereas our nonmetals are gaining electrons, so they're usually negative charge. However, hydrogen, although it's a nonmetal, it's usually going to have a positive charge. As these things gain and lose electrons, sometimes we end up with species that have the exact same number of electrons. And this is a key vocabulary word here. Isoelectronic species are things that share the same electron configuration, but for some reason they have a different radius or size. Okay. For example, argon has this electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. And chlorine used to be 3p5. But if it's chlorine minus, it's gained an electron. So now it's 3p6, just like argon. Same thing with sulfur, -2. It was 3p4, gained 2 electrons. Now it's 3p6. What about calcium, +2? Well, calcium +2 used to end in 4s2. But it says that it's +2, so it lost these 2 electrons. So now it's 3p6, just like the rest of them. So all of these, you get the idea, they all have the exact same electron configuration. So they're called isoelectronic. But they're not the same size. Why? Because they have different protons. So argon has 18 protons. Chlorine has 17. Sulfur has 16. Calcium has 20. Excuse my writing here. And potassium has 19. So which of these do you think is the smallest? As the ratio of protons to electrons increase, the force of attraction on those electrons increases. More protons, more attractive force. So calcium would actually be the smallest out of this set because of its more protons pulling those electrons toward the nucleus. What about the largest in this set? What would that be? Be the one with the least amount of protons to pull in those electrons. Alright, cations are smaller than neutral atoms. Why? Because cations have lost electrons and they usually lose a shell. So potassium is larger than potassium plus. Look how much larger, almost twice as large, because when it becomes potassium plus, it lost the whole fourth shell. Same thing for strontium. When it becomes strontium plus 2, it has lost the whole fifth shell. So now, look, it's almost half the size that it was before. So cations are smaller than their neutral atoms because they're losing an energy shell. Anions are larger than their neutral atoms because they're gaining electrons, and that is increasing the repulsion. Gaining electrons, increasing repulsion. Gaining electrons, increasing repulsion. All right, what about ions as we're going from top to bottom on the periodic table? Well, that's just the same thing, like lithium plus compared to sodium plus. If they have the same charge, we can just look at their location on the periodic table and say, well, as we go down, they're going to get bigger because new shells are added. So even though lithium plus has lost a whole shell, it still has less shells than sodium plus, which has also lost a shell. Okay, so as you go down, they increase in size for the exact same reason as before. New shells are added. Okay, and then we see the same exact reasoning as we saw before whenever we're talking about going down on the periodic table. All right, what if we move from left to right? Now we're talking about cations, moving from left to right. So let's say we're talking about lithium plus and beryllium plus 2 and boron plus 3. Okay, lithium plus, beryllium plus 2, and boron plus 3, if we're moving across like that, they have the same exact number of electrons, but we're adding protons. So they're going to be getting smaller. Okay, why would they get smaller as we move across? It's going to be the same reason every time when we're talking about moving across. We're having more effective nuclear charge because we're adding protons. According to Coulomb's law, if we increase the positive charge, we're increasing our attractive force. And that is going to pull those electrons in and decrease our radius. All right, anions. Now, if you go from being a cation to being an anion, well, an anion is going to be bigger than a cation. But as long as we're talking about all anions, then it still decreases as we move across. Okay, for the exact same reason that we talked about before.